My name is Jenny Tsekwa. I'm on the Kindling team based in South Africa. I'm just going to take us through a few quick introductory slides, as I know that some of you, it is your first time joining us in this space. So I'll take us through a quick intro, then I'll introduce Sam, and then he's going to use most of the time to share with you about our fire experiments. We're really excited for this opportunity. I just have to say up front, this is the first time that we're publicly sharing the results. So it is quite a big moment for us. Well, Sam's saying yes and no. He has had the chance to present at a few other conferences. So yeah, it's for this, I think in this platform, it's the first time. Our director and founder, Danielle Antonellis, she sends her sincere apologies. She's very sad that she's not able to be here today. She's unfortunately recovering in hospital after surgery and emergency surgery yesterday. Thankfully, she's doing very well. But yeah, she's unfortunately not able to be here today. So just to quickly dive in, a little bit about the purpose of this community of practice. For those of you, like I said, who it's your first time, or for those of us who have been here for a while, just to remind ourselves, it's meant to be a space for collaboration. It's designed to bring together professionals from a wide range of disciplines within the humanitarian sector, as well as fire safety and fire protection researchers and practitioners. It was exciting seeing the many different places and disciplines that you come from as you were signing up. And it really does feel that that mission of creating a space for these different disciplines is really happening today in a very real way. So you will see, and Sam will say a little bit more about it, but whenever we give a presentation like this, we're always balancing the socio-technical aspects of the work. And this particular COP is going to be a bit more on the technical side. I'm very excited for Sam to dive into the technicalities of the experiments. And we just give you that little bit of a disclaimer up front that for some of you, it might be your bread and butter, what you discuss every day. For some of you, it might be very new. But whatever the case, we hope that everyone on the call today will take away something of value. This particular COP, and we're happy to be situated within the broader global shelter cluster technical COP, but we're focused on improving fire safety in humanitarian settlements and informal communities as well, and recognizing the complex challenges that are present in those environments. So we've included 2 QR codes there on the screen. In case you would like to know a little bit more from Kindling's side about the COP, and also a QR code for resources on the Global Shelter Cluster website from past community of practice sessions that we've had. We always like to start our community of practice sessions by sharing a little bit of the ethos and kind of what are our community agreements to guide our conversations. And so I'll just run through these really quickly. One is to just keep your microphones muted when not speaking. That's pretty standard. We're all on Teams most of the time, so we know that. Turning your camera on when you speak, we really would love to see people's faces if that's possible when we get to the Q&A time later on. Please be mindful of time and keep your contributions concise. There's opportunities to either use the chat box or at the end of the call, we'll have time where we very much welcome you to share your comments, your reflections, or your questions verbally. Please don't take screenshots or record the session unless permission has been given. We'll actually be recording and sharing the link with you, in which case you're welcome to share it with colleagues. Sorry, if you can just... There we go. Yeah, if we can just note the muting will be very helpful. And then, yeah, I think just a few other points to mention. We always want to credit ideas or words where they come from, participating with curiosity and humility. We're all here to learn, no matter what our level of experience is. And we definitely want to bring in the ethos of respect and welcoming of different perspectives, backgrounds, and ways of working. So treating this community of practice as a co-created learning space. So those are just our kind of guiding principles. In terms of the agenda for today, this is me giving the welcome. I'll share a very brief update just now on the fire safety community practice in terms of what topics we have covered, what topics are still coming up this year. I'll introduce Sam and then hand over to him for the presentation. And then, as I said, towards the end, we'll have a Q&A and an opportunity for discussion, remarks, ideas, and questions. So just to give you a very quick update, the COP was launched in 2024. We've had the opportunity to cover a number of themes together, and a lot of this is coming directly out of context where many of you are working or aware of that are happening around the world. So this particular picture is coming out of an incident that happened back in 2021. So together we're exploring fire safety in humanitarian settings. We had a COP session on learning from fire safety programs in Lebanon, the role of data in improving fire safety, electricity and energy sources, community and human-centered fire safety, institutionalizing fire safety. We then, towards the end of last year, looked at burn prevention, as well as diving into a case study from Nigeria. So that's just a quick overview of where we've been. Some of the upcoming topics that we are hoping to continue to explore together are looking more at community responses to fire, engaging with the local fire services, fire risk assessments, fire investigations, post-fire damage assessments, and a critical review, continuing the theme of institutionalizing fire safety in specific contexts. Those are ideas that have come from many of you. And again, I always like to say this in every COP, we're very open. This is a community space. This is a collective endeavor. So please do send your ideas and your thoughts through in terms of future topics that we can look at together. So without further ado, I am going to introduce Sam to you. I'm really happy to introduce Sam. He's one of my colleagues in Kindling, and it has been a pleasure working with Sam. Sam is a fire engineering researcher with a PhD and an MEng in structural and fire safety engineering from the University of Edinburgh, where he has also taught courses on fire science and dynamics, models for fire safety, and professional development for engineers. Sam's research focuses on fire spread in informal settlements and humanitarian settings. And this has led him to develop a large-scale urban fire spread model, produce fire risk maps with GIS, lead instrumentation for the fire experiments that he'll be sharing about today, designing a materials performance testing program, producing guidance for humanitarian response in contexts like Gaza, and teaching fire science directly to informal settlement residents. So Sam, it's my pleasure to hand over to you. Thanks again for being here today with us.
Thanks, Jenny. Sounded like a lot. I don't feel like I do all those things, but thank you for the introduction.
Always good to remember.
Let me just share my screen quickly. Hoping you can see this. This is where the meeting disappears for me and I can't see anything that's happening. Can you see the screen?
Yep, it all looks good.
Perfect. Wonderful. So hello, everyone. It's great for you to have joined today. It's a pleasure to see some familiar names in the chat and some completely unfamiliar names. I'm looking forward to getting to know you, I suppose. This is the beautiful Western Cape, where about sort of 2 years ago, maybe 18 months ago, we actually ran what was the bulk of our large-scale fire experiment program. And this was obviously a program led by Kindling, but it wouldn't have happened without some very key collaborators. So we worked with Dave Rush from the University of Edinburgh on this. I think he's on the call. He was instrumental in some of the planning the experiments and getting them sort of off the ground when we started them. A huge number of people from Stellenbosch University. We had undergrad students, PhD students. We had Prof. Richard Walls from Stellenbosch as well, was key in sort of helping us source a lot of the instrumentation. And then, of course, FSRI, who funded this work. We're very grateful to them. None of this would have happened without their support, both financially and just generally speaking, being very all the work that's happening with informal settlements and the developing world more generally. So as Jenny's already kind of mentioned, there's quite a diversity of you on the call, and I'm trying to squeeze a lot in today. So I'm hoping you can bear with me a little bit, and there'll be moments for some of you on the sort of humanitarian end of the spectrum where maybe it's quite heavy technical fire science and it might go over your head a little bit. But hopefully I won't dwell anywhere for too long. And equally for the fire engineers and researchers, there might be moments where I'm talking about things that concepts that you're not familiar with in terms of the humanitarian sector. So hopefully there's something here for everyone and we can all kind of get to the same place at the end. A note on questions, we're going to do Q&A at the end. I hope, fingers crossed, if there's time, if I don't talk too much. But I don't mind folk just throwing questions in the chat as I'm talking, and if I can read them quickly and I feel like they're relevant to the flow and I can fit an answer in quickly, I might be able to answer as I'm sort of presenting in general. But anyway, why are we here is the first question. And many of you will be very familiar with this. Some of you may be less familiar. But the fire spread problem in informal and humanitarian settlements more generally is one characterized by, I guess, sort of developing or transient urban spaces where you've got a lot of homes, a lot of shelters packed in quite dense layouts, often using combustible building materials. And the outcome of that is multi-structure fire spread. So fire that doesn't stop at one home, but can potentially spread to tens to hundreds of other homes. And that's kind of the core of what we were looking at in these experiments. Just a very quick couple of examples. The image on the left, that's a settlement called Imizamietu in Cape Town. It's actually about 5 miles over my shoulder, just the other side of the mountain there. I had a fire in 2017, which spread briefly up the hill. I love a little laser pointer here. It started here, spread up the hill, the wind changed direction, and it spread downhill. And in a few hours, they lost about 2,000 homes, and that was about 9,000 people being made homeless. Another context, sort of refugee displacement camps. So this example being the Cox's Bazar in Bangladesh, where we have some of the largest refugee camps in the world, very prone to fires, but different kind of style of materials. So we've got a lot of bamboo materials and tarpaulin being used in that context. Very different to the sort of sheet metal style of shelters we get in Cape Town, but sort of very similar outcomes, massed shelter to shelter fire spread. So the way we kind of conceptualize these experiments, and before we can even get to thinking about conflagration at the scale of hundreds or tens or hundreds of shelters, we have to first understand what are the mechanisms that drive fire spread from one shelter just to its immediate neighbors. And the way we kind of conceptualize this is through the lens of fire spread risk, where we break that down into 3 parts. And we have to have some hazard, which is a thing that can spread fire, in this case, a shelter that's on fire. And there's different ways that it can spread fire, either through high levels of thermal radiation, through direct flame contact to its neighbors, or through the production and distribution of firebrands or embers, you might know them as, which may float further afield and ignite other shelters, not in the immediate vicinity. Now, for these experiments, we were looking particularly at the short-range spread mechanisms, so that's thermal radiation and flame contact. But then just understanding how a shelter burns isn't any indication of whether a fire will spread. You need to know what the exposure condition is, and that's usually just how close are the shelters around it. Can they be exposed to the hazard of the hazard shelter? But then additionally, how likely is that target shelter, how likely is it going to ignite based on its own material properties and the ignition properties of the material it is made of? So that's how we kind of conceptualize the idea. The reason being, that's going to be different for lots of different types of shelters. The world of informal and humanitarian shelters is a big one. You go anywhere in the world, no two shelters are going to be the same. So we've got things like bamboo mat and tarpaulin. We've got mud shelters with thatched roofs. We've got more formal brick shelters. We've got split bamboo down the middle bottom here. Sorry, I've turned my pointer off again. So this is a split bamboo material here. We've got thatched walls with a thatched roof. Sheet metal will often be used in roofing, but then we also have entire shelters that are, potentially more than one story that use a lot of sheet metal. And of course, tarpaulins, tents and tarpaulins, which are sort of ubiquitous, if that's the right word, to many regions in the world where there's humanitarian response. So obviously we can't test everything. We're not going to test every single unique style of shelter. So one of the first parts of this work, going back sort of 2 or 3 years, was actually trying to build a database of what shelters are actually out there in terms of materiality. So we spent a lot of time looking through UN reports, IOM reports, a bunch of different documentation primarily from the humanitarian space that had images of different shelters and had some data on what materials they're made out of, how many doors and windows they have, how many stories they have, things like this. We managed to get to a database of just over 450 unique shelters, and these are taken from over 90 countries. So we're not restricted geographically. We've got shelters from Africa, Latin America, Asia. We've got even like the refugee camps that we have in Europe are captured in the data as well. So I think just about every continent is represented. And what we really were filtering for is across the world, what are the most common prevalent combinations of wall and roof material. From that, we sorted it into 14 core shelter experiments that we wanted to do. So this is a table. I'm not going to go through this in detail, but generally the 14 core tests we split into these 5 different categories based on what's the combination of combustibility of roof and walls. So, and I don't mean the like degree of combustibility. I just mean, is it a material that burns? And so we have non-combustible wall with non-combustible roof, combustible walls with non-combustible roof, etc., etc. And then there's 6 extra experiments that we did looking at things like experimental repeatability. We had a couple of quite opportunistic experiments on wind, and then this is more of a niche kind of experimental process. How does the shape of a thatched roof affect things? So 20 big shelter experiments in total. So what does a shelter experiment look like? Well, the first thing you'll notice here, I've been talking about fire spread, but in any single experiment, we were only burning one shelter and measuring lots of things about it. So every shelter had a floor plan of 3.6 meters on the long side by 2.4 meters, and it was 2.4 tall. They were all positioned on this platform here, which contains a 6-ton capacity scale. So we're measuring the mass of the shelter, which can give us mass loss rate, which roughly can help us sort of analyze how much energy the fire is releasing over time. So we call that the heat release rate. But if you're just measuring the mass, it's a bit of an approximation. It's not particularly accurate, but we can't do sort of accurate heat release rate measurements in a big outdoor context. I'll start with thermocouples. So inside we take a bunch of temperature readings with thermocouples just to kind of understand the growth of the fire within the shelter. Externally, what we're looking at is the dominant part of our test program is these instrumentation rigs here, each of which carry 2 thin-skin calorimeters for a total of 60, call them TSEs, 60 TSEs, for the full range of instrumentation. 2 of those are accompanied with heat flux gauges, And then we had cameras in various positions looking sort of along the axis of a wall to view like the flame extension from the openings, and various other cameras just sort of in general views of the shelter as it's burning. The last thing to note is probably not in view at the moment, but we had 3 tall sort of wind measuring instruments. One's just coming in here. So we've got devices measuring wind direction and wind speed on these, just in the sort of general field around the shelter as it's burning. So I mentioned these thin skin calorimeters are a core part of the testing program because they measure heat flux, and that's the energy transfer, the rate of energy transfer these various positions away from the shelter. So that's the if I'm standing in the position of one of these, that's the heat that I receive. If I'm standing looking towards the shelter at that position. TSEs are, if you're a fire experimentalist, you might be thinking, oh, they're a bit, they can be a bit temperamental, and you're right, they can, but they're cheap and they're easy to mass produce because each one is just a small square of this vermiculite. It's an insulating material with a little stainless steel disc with some thermocouple wire welded to the back. And really, they're not actually measuring heat flux. What they're measuring is the temperature, and then we have to back calculate heat flux once we have the data. Now, the critical part of, or one of the critical parts of our program was pairing 2 of these, one 2 meters away from the window and one 2 meters away from the door. And we paired it with a heat flux gauge. So we're equating the 2 and saying at this position, you know, the heat flux that the heat flux gauge receives, and it's quite a high fidelity reading, is effectively equivalent to what the TSC is going to be seeing. And in a moment, I'll explain sort of how we then calibrated our entire TSC set to the heat flux gauge data. The reason for this, and this is, I'm sorry, is my most like nerdy technical slide. The reason for this is the way that TSCs calculate heat flux. So the theoretical proper way to do it. Sorry, this question's just come in. I think I might have a look. I'll answer that later. I'm not going to answer it now. So yeah, there's this big complex equation that we have to satisfy and calculate to get the heat flux at the back. The problem with this equation is this little c here. This is a calibration factor that should be lab determined. You're supposed to take a bunch of your TSCs, take them to a lab, put them in front of some sort of radiative source and calibrate them very carefully to get this one calibration factor. Firstly, we didn't have the ability to do that. And secondly, even if we used a calibration factor that has been used for very similar TSCs in the past with the Irish Fire project that Stellenbosch and Edinburgh did, what we get is across the full range of comparison between heat flux gauge and TSCs is a not particularly good prediction of what the heat flux gauge data is. So across all the experiments, we have something like 20,000 data points where we have a heat flux gauge reading and a calculated TSC heat flux. And there's problems with how this was working. Notably, the TSCs were not good. This is the TSC data here, and this is the red lines, the gauge data. The TSCs were consistently not good at capturing the highs, the peaks of the heat flux, which is this sort of region of this graph. And then also they weren't tailing off fast enough. So they were predicting too high heat fluxes for too long, which is sort of this part of data on the graph. So what we did is we ran a regression with the heat flux gauges against the TSC data and produced a correlation that much better fit the TSC data to the heat flux gauge data. And as you can see, just in this particular example, our TSC line here, the blue line, is generally speaking fitting the heat flux gauge data in a much better way. So for those of you in the sort of more fire science end of the thing, end of work, that's how we extrapolated or calculated TSC heat fluxes for our full range of TSCs. Now, fuel load, this is going to kind of flip from what I was saying before of fire scientists. You probably are kind of be bored now. If you've worked in experimental fire research, you'll know what a wood crib is. You know why we use them. But to those of you in the humanitarian sector, this might look a bit weird. So we're not, when we talk about a shelter on fire, a large amount of the fuel that a shelter that's burning in that fire is not the shelter itself, but it's also the stuff that's in the shelter. So that'll be people's belongings, it'll be furniture, it'll be whatever. This does not look like furniture or people's belongings. This looks like two piles of wood. You're never going to have this inside someone's real home. But the reason we use these is experimentally is they give us a very good way of being highly repeatable in the fire that we're producing. Two wood cribs that are built in the same way should produce a very, very similar fire to one another, which means across experiments, every time we're testing a new shelter, we're exposing it to the same internal fire as the last. And the other kind of side of it is that we can replicate the total sort of thermal load that we would expect in a real shelter, and we can replicate the amount of energy in an equivalent amount of timber, and that's what we do here. So we went and found data on fuel loads, and then converted that to a required amount of fuel for our shelters, and turned that into wood cribs, and we get a nice repeatable fire. Each fire would start by our firefighter here igniting sort of 8 small igniter packets just to get the cribs going. But yes, that is why we burn a massive amount of timber inside and not things like sofas or chairs or mattresses or whatever. Okay, so quickly just to cover some of the initial findings. So this was data as we presented it at some conferences last year. And this is really just like the hazard, the quick high-level findings of hazard. How does a shelter burn? What kind of immediate heat fluxes is its environment being exposed to? So the next 3 or 4 slides, what you're going to see is a shelter burning at the top. Down here, we've got what we call a heat flux map. So we're taking our heat flux data, plotting it spatially as time progresses. And you're also going to see the mass loss rate, which, as I said, we're kind of equating to heat release rate. But as a comparison between shelters, it just gives us an idea of how much and how fast the fuel is burning. So I'll just run this first one. And this is our kind of nice base case sheet metal shelter, very much of the style we get in Cape Town and other places. And this, for the fire engineers among you, behaves as we would expect a sort of fairly conventional compartment fire to behave. So we get a slow growth period, then we hit flashover, which is our accelerated fire growth, and then after that we've got, as you can see, indicated by the heat flux data, where our window, so our door here at the front and our window at the back, where we've got those openings, there's flames extending, obviously providing a lot of heat to the environment there. But you'll see we hit this sort of steady state where we were losing about half a kilo a second of fuel. And this is kind of consistent for any of the shelters we did where we had what we call non-combustible facades. Even if, there's a timber frame holding this thing up, what we're saying is we've got sheet metal on the outside. The other shelters we did were cement block and mud walled shelters. And we get a fairly consistent hazard profile of a normal compartment fire and then external flame from the door, the window. But when you add in combustible materials, we're obviously going to get, we've done 2 things. We've added fuel that can burn, so we're expecting a higher mass loss rate. But then we're also, we've put some of that fuel on the external face. So we're going to expect burning on the outside of the building. So I'll run this. Immediate key findings is that you'll see in a moment, but the mass loss rate is going to peak at about triple that of the conventional compartment fire. Instead of having high heat fluxes exclusively located where the door and window are, you'll see we've got this much wider distribution of high heat fluxes in all directions, right? Now, this is our timber shelter. We did see some similar behavior, not fully identical. There's a difference in kind of the rate at which they burn, but we saw similar behavior with a bamboo mat material and a split bamboo material, where the fire transitions to the walls burn away, but expose everything to quite high heat flux in all directions. Um, kind of flipping it the other way now, with a combustible roof but non-combustible walls. And we start to see something of a trade-off developing. Now, in this case, we progress as if we're going to a compartment fire. But then once the roof has started burning through, you'll notice that all the hot gases can vent through. The roof itself is obviously burning, but you don't get that high hazard concentrated around the openings or immediately adjacent to the walls. You've kind of relocated the high hazard area upwards to the level of your roof. So if you're measuring at the level of the shelter, what you see, or what you would have seen here, I might actually dial it back a little bit. What you'll see at this point here is much more distributed heat fluxes. So they're a bit lower, but more broadly distributed than if they're just around the openings. Back to my laser pointer. I love it. Mass loss rate. This was unfortunate. This shelter was actually too heavy for the scales, so the mass readings only kicked in halfway through. But again, we can say at least at one point the fire was triple the, or was consuming 3 times the mass of the conventional compartment fire. Again, then obviously with a steady decline as it decayed. And then the last one I want to present to you in this format is the a combustible walled with a combustible roof shelter. And I've isolated this one particularly as probably like the highest single hazard that we saw in the experiments. I'll just run it. So things you'll notice, so look for the mass loss rate to spike to a very high level. So we're talking 6 to 8 times that of the compartment fire, which means we're consuming 6 to 8 times the amount of fuel, which likely means we're releasing 6 to 8 times the amount of thermal energy to the environment. In this case, we had a very well-defined vertical plume. We have very high heat fluxes in all directions. We were measuring gas temperatures of 1200 degrees within the plume. And perhaps the biggest indicator that this was a hot and dangerous fire is that we melted or damaged our camera that was sat, 10 meters away. And I don't know what happened, if it distorted the lens or something, but a hot fire, you could really feel it. The highest hazard, the highest single hazard that we measured. But I want to come back to this word hazard. I keep saying hazard, and I'm being very particular about that. And I'm saying from a shelter, from knowing how a shelter burns and where it's, what like levels of heat it's releasing, all we're saying is how hazardous that single shelter is. The next thing we need to do is connect that to vulnerability, because different materials have different levels of vulnerability, and so are going to ignite under at different speeds under different conditions. So the other side of the work was we were working with a commercial lab in Cape Town who had a cone calorimeter. Again, fire scientists, you can probably switch off this next part. But for those of you who aren't familiar with a cone calorimeter, what we do is we take a small sort of 10 by 10 centimeter sample, so it's not large. We place it in a sample holder. It sits underneath the reason it's called a cone is this heating coil is conical, and it's an electric coil that heats up, exposes our sample to whatever level of heat we want it to. And then we also have this pilot spark here, which sits there and constantly sparks, as you'll see in a moment on the right-hand side. Now, as the material is heated, it starts to pyrolyze, it releases fuel gases, they mix with oxygen at the surface of the material, and that spark sparking there is providing energy to cause an ignition. But under different heat fluxes, under different levels of heating, the rate at which a material ignites is going to change. Sometimes it'll take 20 minutes to ignite if we're at a very low heat flux. At high heat fluxes, it might take 10 seconds to ignite. But it's all to do with how fast can we get heat into the material to release fuel gas and ignite it at the surface. So since last year, the direction of travel has really been in trying to connect the hazard data, so the heat fluxes from the shelter scale experiments, with this ignition data. So we have ignition data on all the materials that we were using in the shelters. And the way we joined these dots was to say, well, at any given location where I measured heat flux, I have a heat flux profile in time, just exactly like this, where over time we're waiting for the fire to grow, the fire grows, and then it starts exposing its surroundings to a varying level of heat flux. Now, if I pick a particular material, um, and then the way we've done it is say we've got threshold time, so sort of every 2.5 kilowatts per meter squared, it takes X number of seconds to ignite, is if I then compare that to my heat flux profile and see that a certain threshold has been ignited for, has been exceeded for a sufficient amount of time, then we flag ignition and we say ignition for this material at this location would have happened in this time. So here's just a sort of rough visual example. We did far more thresholds than this, but the idea is that, say, for this particular material, it needs 2,600 seconds to ignite at 10 kilowatts per meter squared. That's like, what, 40 minutes or something like that. Or it needs 5 minutes at 20 kilowatts per meter squared, but it only needs 40 seconds at 37.5, and that was the particular threshold that was triggered in this case. So as I say, we're thinking about trying to make predictions of fire spread time. So then we come up with this idea of time to ignition mapping. So instead of just mapping heat flux, actually theorizing what material is positioned at all these various locations around the shelter and trying to predict how long they take to ignite. The first thing I have to clarify is time to ignition in this sense. We've obviously had to pick like a reference point. So as a reference point, we're taking the start of flashover and we're saying if the origin shelter has started flashover, how long does it take after that until it's spread to its neighbors? I want to give a visual example of that. So consider we have a shelter. Just for argument's sake, let's say it's the experiment we did with bamboo mat wall and it's got a thatched roof on it. Imagine it's got some neighbors in its immediate environment. We can then plot all that time to ignition data that we've calculated from our heat flux data and our material ignition data. And then I could start observing things about, well, if I had a neighboring location here, and to clarify, say, imagine it has neighbors and they're all the same material. So they're bamboo mat with a thatch roof as well. So I use the bamboo mat as my most vulnerable material. If I have a shelter positioned here, that's sitting comfortably in this nice big red zone here, which corresponds to it's going to ignite within a minute of the first one hitting flashover. And if this one, if I had this one sitting here, it's sort of on the borderline. It's just on the edge of where it could spread fire within a minute. But actually, outside of that, if it was just a few centimeters back, maybe it wouldn't have even ignited at all. And then this one, yes, it looks like it could ignite, but maybe somewhere in the region, 5 to 7 minutes. So this is just to give you an idea of what this data is actually, what it actually means. But with this kind of frame of reference, we can then think about, well, what about changing materials? So obviously we had an experiment where we had a bamboo mat wall with split bamboo roof. So let's say I change my hazard data, that changes the distribution of ignition times. So this one is still within the sort of 1 minute zone here. It still has a big overlap with it. This one is maybe pushed back. It would still ignite, but only after 7 minutes. And then this last one here, no ignition at all. It doesn't sit in the ignition data. I could even extend this and say, but what about these neighbors? What if I change their material and say, no, actually, I think they're made of timber. They're not made of bamboo mat. And then that changes the way we process the data again. And that shrinks that sort of time to ignition region even more. And now we have two sitting outside the ignition zone and one potentially still igniting quite quickly. So hopefully that kind of gives you an idea of what this data means and what it's saying. And then from this, we've got some fairly valuable insights. So the first is maybe something we kind of expect already, but with these non-combustible materials, in both these cases, I assume timber is the exposed material. But for argument's sake, a sheet metal shelter, this one was slightly impacted by wind, so we did have slight flame extension out of the door rather than the window. But generally speaking, if we have these non-combustible facade shelters, the location of openings is your real important point, right? So you're always going to have external flames from any open windows and doors. And it's in the immediate vicinity of those where you're potentially at risk of fairly rapid fire spread times. We move on to combustible wall materials. So now this is the three sort of bamboo mat, split bamboo and timber that I want to talk about. That is it, Dennis, about wind flows. Great question. I'm going to come into wind in a moment. So bamboo mat as a material, very ignitable. We saw that from our cone calorimetry testing, but it also, when in the shelter test, when it hits flashover, the walls burn away extremely quickly. So you have a very short, sharp, quite extreme hazard peak. You have a very ignitable material. That means over short distances, very, very quick fire spread. So we have, for our bamboo mat wall shelter, we have fairly large vicinity around it, sort of 1 to 2 meters, where we're expecting fire spread within a minute of that first shelter flashing over. Compare that with, say, the split bamboo material that we used. It wasn't as easy to ignite. It took longer for the fire when it hit flashover to transition to the external walls. And so we get data that, okay, albeit in close by the sort of door and window, we're still talking sub 3-minute ignition times. But then we have this nice decay, and a bit further away, we're talking, yeah, okay, ignition might still happen, but it's going to be happening 7 to 10 minutes. It's going to be taking a lot longer. So even though these look like similar total areas around these shelters, we have to take into account the fact that fire spread rate is a very important thing. And the bamboo mat has potential to spread fire a lot more quickly, despite the fact that we could look at these two materials and say, well, they're both combustible, they're both bad. The other comparison is timber, which sits sort of nicely between these two, where we would have seen fairly rapid fire spread to a neighboring timber shelter. If it's sort of up against the front or back wall, we're talking 2 to 3 minutes, and then quite a wide range where you'd expect ignition after about 3 minutes. But again, we get out beyond 1.5 meters to 2.5 meters, and we start to be in the realm of it's probable that fire might not spread at all. Now, thatch, I want to talk about. Thatch, again, identified it as a very high hazard. And this data got me questioning. This is, I have time to ignition data at every single point in the measured space. So my TSCs were only up to 3 meters away from the shelter. And I filled that entire space with data that says, yes, a neighboring thatch shelter could ignite here. So I have to ask the question, well, is it possible that further away I could ignite a thatch shelter? And so with a little bit, I'm a bit cautious about this. It's extrapolating, data outside of the measured region, which I don't love doing. But if we do extrapolate our TSC heat flux data out and then calculate the times to ignition, sorry, that's the 3 meter distance boundary. If I extrapolate it out and see how far I can get it, if I put that same boundary, that's sort of equivalent to that. So this is the same data, it's just slightly less clean, and I haven't quite correlated the color scale, right? This is exactly the same data on these two plots. This is just to further distances on the right-hand side. So theoretically, we're looking at fire being able to spread between two of these thatch shelters at, we're over 3 meters there, we're pushing 4 meters, getting close to 5 meters. So we're starting to talk about fairly serious separation distances if the goal is complete prevention of fire spread. Yep. And then the final thing I want to land on with these is the idea of fire spread risk as a concept in the first place. It's like, what do we actually mean? Because the separation distance can do two different things, right? In the case of our bamboo mat wall, what we have is an immediate area of very, very fast fire spread. But after that, because the walls have burned away quite quickly, there's a pretty steep gradient to the point where there's no fire spread at all. So if you imagine a shelter here versus a shelter here, our experimental data is saying this one's going to ignite in a minute, this one's not going to ignite at all. So it's a very fire spread rate driven problem. Whereas for the thatch, and I've just got the sort of 3 meter data up here, but I've just shown you potentially we're looking at fire spread distances over 3 or 4, maybe even 5 meters. It's a distance problem, right? So this shelter is not dangerous because it can necessarily spread fire quickly, because we see it actually takes longer to spread than for the bamboo mat shelter. But it's a big risk because it can spread fire far. And so there's kind of two different angles at which we can look at separation distance as a mechanism for potentially reducing fire spread risk. Okay, thanks for the question, Venki. I'm just seeing you talking about contents inside the shelter. I will hopefully answer that at the end. I'm not going to come back to that now. But anyway, quick conclusions from these sort of time to ignition maps. So if we have non-combustible facades, as I've said, locations of windows and doors, very, very important. We're going to get external flames from the openings. They're going to be the main drivers of fire spread. Secondly, combustibility and ignitability are not equal concepts. Lots of things can burn, but they can take very different amounts of energy, sort of generally speaking, to get them to ignite. So as I've shown with the sort of two bamboo materials and the timber, is two different combustible materials can give very, very different outcomes. In our extreme cases, this is going back to our thatch case, we might get fire spreads beyond 3 meters, potentially 4, potentially 5 meters. And with that in mind, separation distance is not necessarily a silver bullet to the fire spread problem. It is something that we can leverage to reduce fire spread risk, but let's say in the example I give here, that 20 centimeters extra separation distance, for instance, is not going to give you the same benefit in different contexts. So in some cases, it might be the difference between very fast fire spread and fire spread not at all. But in some cases, it might be you delay a fire from spreading for a few seconds, a couple of minutes. And it's all dependent on materials of what shelter is made from. But what is not included in this analysis yet? And Dennis, you were on to something there, because I'm going to talk about wind now. So all of these, I even mentioned that there was slight effects of wind in the sheet metal shelter, but generally speaking, every experiment I've talked about so far, we were conducting in what we consider to be low to no wind conditions. So that was something in the range of 0 to 2 meters per second. Any day it had those wind conditions, it didn't feel like a windy day, let's say. But wind is very powerful. And in a couple of days where we were hoping to test, we had extremely high winds that kept blowing our instrumentation over. So those big tall rigs that we had, they all got blown over. We stood them back up again. We supported them with big heavy cement blocks. They all blew over again. And we got to a point where this isn't safe. We can't actually measure data safely in this wind environment, but we still want to see the impacts of wind on a shelter. So we stripped back all the instrumentation and we burned them anyway. And this was the result. So we did a repeat of our sheet metal shelter on a day or on a period where the wind speed was about 5 meters per second on average, but we did get gusts up to over 11. And we're looking at, large extension of the external flames. In this case, it's obviously quite turbulent and they fluctuate a lot, but we're getting flame extension up to sort of 3 meters there. Now we go back to our combustible materials, or the bamboo mat. Again, a very short, sharp period that it took for all the bamboo mat walls to burn away very quickly, but under these sort of driven wind conditions, we have a very large extension again of the flames from the shelter. Looking at over 4 meters here. The scary thing about this one in comparison to the first is, in the first, that's a jet that's approximately equivalent to the width of the window that it was projecting from. The bamboo mat, we're talking about a 3 meter long wall projecting flame 4 meters. So significant energy output there. Dan, great question. Were we able to collect mass loss data? Yes, it's horrible. It's super messy because the wind played havoc with the readings of the scales. So I can't remember if I tried processing it, but yeah, the noise in the data was like far too high to have anything meaningful from it. But then we also found that wind, even lower wind speeds, is still significant. We might not call it wind per se, we might call it just a gentle breeze, but we set out to do some repeatability testing on our timber shelters. So I think we did 3 of them. I'm going to show you 2 of them, the lowest wind speed and the highest wind speed. Fortunately, they were all occurred with wind in the same direction, which was pure luck, to be honest. The difference was just the wind speed. So here, what you're looking at is the door side in a very low wind day with flames projecting to about 1 meter from the door, but on the window side, flames also projecting to about 1 meter. The heat fluxes I've noted here are just the sort of peak heat fluxes at 2 meters away, as measured by the heat flux gauges. So, I mean, the story of this is really quite, I would say, quite like symmetrical fire. The hazard is pretty equivalent on either side. But we go up to 1.74 meters per second wind speed. So again, it's not windy. It's still a breeze on the ground that day. I would have been like, it's not windy at all. But it's still enough to impact the fire. So on the door side, we're now looking at flames sort of 2.5, maybe even to 3 meters from the shelter. And we more than doubled the peak heat flux that we're receiving 2 meters away. On the flip side, the window side of the shelter, we virtually eliminated flames from the window here, and we more than halved our peak heat flux 2 meters away. You also notice the difference in the fact that this wall is barely burning at all compared to the back wall, which was more sheltered and completely burned away really quickly. The other note of caution is firebrands. Now, we didn't do anything, unfortunately, in these experiments to quantify firebranding. There is a lot of research out there on firebrands, a lot of very good research, not necessarily any of it applied to informal or humanitarian context yet. And unfortunately, we just weren't resourced to kind of do anything to measure it. There's a lot of steps in the process looking at sort of the production potential, like how many firebrands are being produced, how are they being distributed, how far away are they being distributed, and then how does something ignite in response to having firebrands landing on it. We unfortunately didn't have the resources to do any of that. So there's a lot more research needed in this space. I think what we can say is it was very obvious which materials were producing them. So namely the bamboo mat material and thatch material produced them in high numbers. But yeah, as I say, not something that we've quantified, but something to be aware of as a hazard for some materials potentially. Then I kind of want to take a bit of a left turn quickly to say, what are we hoping to do with our time to ignition data? And the sort of latest work we're doing is we're trying to develop essentially a settlement scale risk model using the experimental data to kind of visualize how fire spread risk can then play out at the grander scale. We're talking about looking, at different, there's obviously completely virtual settlement, and the model is very much a work in progress at the moment, so don't read anything into what you're seeing here, but we want to be able to look at the grander scale. What if we change separation distances? What if we change where the openings are located? What if we change how shelters are oriented relative to one another? And how that changes the fire risk score metric that we're sort of trying to develop at the moment. And then, of course, the other comparison to be made is how does material impact fire risk in this element? So if I change one material to another, what is the sort of tangible, quantifiable impact on risk in the settlement overall? As I say, work in progress. Hopefully there'll be more in the coming months coming out of Kindling about that. So that's kind of, I'm going to park the large scale experiments for a moment because I'm sure some of those of you in the humanitarian sector might have been screaming at me this entire time saying, what about tarpaulins? It's good news and bad news on that front. The good news is we've tested some. The bad news you'll find out in a few moments. But for me, I, as a fire researcher, had never really confronted tarpaulins before. And coming into these experiments, there's sort of a few questions that I had. Those being, well, in the documentation, I'm seeing that the tarpaulins are being given fire certification, and based on some test methods, I wanted to know what are those test methods and do they work? Does the evaluation of materials hold up? And then how does the tarpaulin behave when we put it in a shelter scale and burn a sort of tarpaulin tent? So two test methods that are used. Some of you, I'm sure, are going to be very familiar with these. We've got the single burning item test, or as you may be more familiar with it, the EN 13823, or whatever it's known in the country that you work in. We also have something called the CPAI 84 test. It's not a construction industry standard. It's been developed and used by the textiles industry. However, it is almost identical to the ISO small flame test. So if any of you are familiar with the ISO small flame test, they are very, very similar, apart from some tiny little differences. But for the sake of today, I think it's useful to just equate them to one another. So firstly, the single burning item test. For those of you who are less familiar with it, what it is we take a large sample of the material. Exact dimensions have slipped my mind, but I think it's something like a meter by a meter and then 0.5 meters by a meter. And we have two panels of the material. That material is then exposed to a very well-defined gas burner. So we know exactly the size and heat release rate of that little fire. And among other things, the test is looking to quantify the material's response in terms of does it propagate fire spread along the long wing? Does it produce smoke? And does it produce lots of burning, flaming droplets that are dispersed in the environment? So this is what it looks like. This was one of our samples that we had tested. So this is a UNHCR tarpaulin with fire retardant in it. And this is a bit of an awkward camera angle, but it's one of the best we have. And it's sort of looking along this way. We're looking, if this is the short panel here, that's this short panel here. This is the gas burner. This is the gas burner here. So initially, the gas burner is ignited. And what we saw with tarpaulins that we were testing is really not much. The material itself tends to sort of shrivel and warp when it's exposed to heat, and it moves away from the sample. Now, I think we did 12 repeats, or maybe 6 repeats of this material. I think 6 repeats of this material and 6 of another tarpaulin. And in almost every single case, this is exactly what would happen, was the tarpaulin would warp away from where the heat was, and you can see the exposed board behind it. In one case, a small flamelet did manage to establish on the sort of damaged edge of the tarpaulin, and very slowly over a period of about 10 or 15 minutes, this long panel slowly burned away. But generally speaking, all of these samples did this. And because of that, I won't go into the details of it, but because of that, they all would have received a pretty reasonable classification, as in this is a fairly fire-resistant material. But I have to sort of look at this and challenge it and say, but I don't think a good rating is necessarily an indication of the material's performance. I think it's an artifact of the the way the material moves away, and it sits there not being exposed to very much heat for 20 minutes because it's moved away from where the heat is. So again, I kind of come away from this with more questions than I have answers. So the next testing method, CPAI, it's essentially a sort of foot-long strip of the material clamped in the sample holder here and exposed to a very small flame. The principle is that you expose it to a flame for, I think it's 12 seconds or 15 seconds or something like that. The idea is when that flame is removed, the sample should self-extinguish. It shouldn't propagate the flame any further. So here we have the sample being the flame being applied to the sample, and you'll see within a few seconds, it seems like there's already flame fairly well established on the sample. Now, this is the same material that we saw in the SBI test, where when it had the ability to, it just moved away from the heat. Here, where it's held over the heat, and it does catch, we had this sample being destroyed in like 20 to 30 seconds. And again, we do a bunch of repeats. I think we did 8 in this case. In every single case, the material, the flame established, and took over, and the sample was entirely burned away. So now I sort of find myself in the position of asking, so is this tarpaulin just horrible and flammable, even if it's got flame retardants in it? Because this tells me the material has failed and shouldn't be used as a safe product. But then let's scale up to the shelter and do a shelter experiment exactly the way we did everything else, by setting the fire on the cribs inside and watching how the shelter behaves. So are we going to see behavior where the material just moves away from the heat, or are we going to see it igniting and taking hold? That's the sort of interesting question when I'm watching this footage. But you might notice already that we've started to get some movement up here. The tarpaulin is peeling back off the frame. And you'll see, well, I can just about see some very light smoke emerging here. But then you'll start to see the tarpaulin pinging back everywhere we sort of connected it to the frame. The material is like shrinking and tensing, and it's tearing away from those connections. And slowly over time, the material just kind of tears apart. You'll notice that the crib is, you can still see a lot of untouched wood there. This is still a very small fire relative to what we've had in other cases. The crib is not even fully developed, and we basically don't have a shelter anymore, right? We're losing all our walls. Maybe the optimist in me says, "Oh, none of it's ignited yet." Well, that's great. And I do tend to be optimistic, having seen these experiments. Just another view. This is, sorry, let me start the video. This is exactly the same experiment. We're just looking up through the door here, and this region up here is just the roof space where there'll be lots of smoke collecting, and you'll see there that the roof has torn through. There's a big gap formed, and all of our smoke will be venting out. Now, from our thermocouples, from the temperatures of the smoke, we were at about 200 degrees Celsius, which in fire terms is not particularly high. And so we're seeing the shelter, the tarpaulin, being compromised very early on, but not igniting, potentially. Dave, I just noted your question in the chat. So how does fuel location in the shelter impact the ignition of the wall materials? Now, that's a very good question. And that kind of brings me on to my conclusions about tarpaulins, is really that we don't know enough yet. And it's kind of a case of, if the fire starts on fuel in the shelter, does it ignite the tarpaulin early enough and at low enough exposure? Because you saw we needed that very small flame to sort of gradually get the ignition going. Whereas if you suddenly expose it to a lot of heat, I think its tendency is to move away from the heat source. So when I said I had bad news on the tarpaulins, it's not bad as in they're not great. It's bad as in they really confuse me, and I don't quite know what correct answer to give with these. I do think the SBI test isn't an adequate test for the material. I don't think the test method was designed to be testing materials like tarpaulins. I think there's potential to look at different standard fire testing methods for tarpaulins. There's also a need for research. Dave, I know you're kind of onto this already, a need for research of tarpaulin in combination with other materials, not treating it as a material that's always used on its own, but actually seeing when it's used with, for instance, bamboo, what kind of behaviors does it exhibit? And then a real big question mark is if we're doing these tests with non-fire retardant tarpaulins, we can't really fully assess to what degree they are better if we can't test non-fire retardant tarpaulins. So, I mean, I'm sure nobody here is going to be like, yeah, sure, here's a bunch of non-fire retardant tarpaulin for you to go and burn. But at some stage, you can't assess. I know particularly there's maybe a bit of debate about are fire retards needed? Do they pose health risks? Whatever. I'm not sort of super involved in that debate, but from the fire perspective, we can only assess the gains in fire performance if we know how the non-fire retardant and tarpaulins burn and can be quantified in a like robust and scientific way. I realize time is swiftly moving on. Great, I have 2 slides left. This is one that again, people on the call are going to come at from 2 very different angles. So I want to talk about what the current sort of fire safety guidance is for the humanitarian sector. So those of you who work in that space, I'm sure you will be very, very familiar with the Sphere Handbook. Those of you that are sort of practicing fire engineers or researchers are going to maybe have a very different opinion of this as a document. So Sphere Handbook is a document that advises on all manner of features of sort of humanitarian camp design, shelter design. It includes guidance on fire safety. I'm sure many of you are very thankful for that guidance. There are fire engineers on this call that are used to working with fire design codes that are hundreds of pages long, that have stuff to do with evacuation and smoke control and alarm systems and stairwells and all this complex stuff. So you are familiar with robust fire safety guidance. The grand total of the fire safety guidance in the Sphere Handbook is 9 lines of text. Now that 9 lines of text, I'm sure is very helpful for some of you, and I think there's going to be others of you on the call who are thinking, is that it? That's absolutely nothing. I'm not putting this here to critique the guidance in any way. I think it's just hopefully so that across the spectrum of people here, you can kind of start to realize, for those of you who are in work in fire research, how like underserved this sort of area of fire engineering is. I want to sort of draw attention to 3 of the clauses in particular, again, just to kind of compare to what our experimental data now says. And thinking about how we might actually, Kindling as an organization, start contributing to contextualizing this guidance and maybe seeing ways in which we can update it. So the first is the classic sort of separation distance problem. Buildings should ideally be double their height apart to prevent collapsing structures touching one another, but failing that, and obviously that's quite a high bar to get over. Failing that, then 2 meters is your safe distance. I think I've showed enough data today to show that fire spread beyond, and fairly rapid fire spread beyond distances of 2 meters is feasible. And so 2 meters should not be viewed as this perfect standard. Particularly, 2 meters for some materials might be adequate. For others, it might be nowhere near adequate. Fire breaks, 30-meter fire breaks every 300 meters. So I said we haven't done much to quantify firebranding, but we know from firebrand research in other areas that firebrands are perfectly capable of exceeding 30 meters. So if that is the intention of the firebreak rule, just not looking like 30 meters is going to be particularly beneficial. But from the other end, because we're not exactly sure what the intention of this rule is. From the other end, if you're looking at close range fire spread mechanisms, so that's Um, Radiation, that's flame contact, 30 meters is more than enough. It's way beyond, I was talking about thatch as the most hazardous shelter type, and I'm worried that it can spread over 5 meters. 30 meters is more than conservative for preventing fire spread by radiation and flame contact. So there's potential discussion to be had here around, is this an efficient use of space? Could we rather take that 30 meters and distribute it elsewhere so we can increase separation distance at the local level between shelters, rather than having these sort of large unused space in settlements that doesn't have a particular utility from a fire spread point of view? And then the other thing I want to highlight is this idea of fire resistant construction materials. At face value, perfect, but obviously I'm aware that many of you will be working in conditions where this is not possible. Okay, I'll come back to the 30 meters in a second. The fire resistant, sorry that you've derailed my train of thought, Danielle. Yeah, so there's what I want to say about this idea of fire resistant materials is, okay, A, you're possibly not going to have access to fire resistant materials, and B, even with materials that are not necessarily fire resistant, there's still a huge spectrum of potential outcomes. I showed you that with the different combustible materials, and sometimes you'll get rapid spread versus sort of slower spread, even if both materials are combustible. So hopefully we can start providing context about what's the kind of spectrum of risk within different but still non-fire resistant materials, knowing that you can't always obtain fire resistant materials in every single case. Last slide, I promise. So I'd like to end on just kind of what have we done with this data, and what's next for Kindling in sort of different projects or different outcomes we want from this work. So if you go to our website, you'll find that we published a series of short videos kind of covering the experiments. They were produced by a professional videographer from South Africa who is absolutely phenomenal. He's done an amazing job of capturing the work visually. So if you want a more visual kind of view and of the experiments, then I could provide here. I highly recommend those videos. We've taken the sort of technical parts of this work to some conferences, and we've also run what we're calling Fire School, which has been a training program for residents in Cape Town, where a lot of things are covered. We touch on the experiments. We obviously don't go into maybe the level of scientific detail that you'd expect here, but we do try and relate some of what are these quite complex fire safety concepts in a nice simple way. So talking about impact of materiality, impact of door and window locations, and things like that. Looking forward, we are working on a guidance document. I sort of put that in quotes because we are trying not to write it in a style of you must do this, 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 and this, because we know that's not necessarily helpful, but using the data to try and contextualize decisions that you might be faced with. So trying to actually indicate the spectrum of fire spread risk that can occur and try and point you in the right direction to alleviate fire spread risk, potentially not fully eliminate, but how do we make progress? Potentially going to run Fire School again, but for professionals, as we're calling it. So that could be city planners, engineers, architects, council people, whoever's interested really, and to try and communicate what can be quite complex technical topics, but distill it into sort of simple and practical ways for people to actually implement in the work they're doing. As I already kind of shown, we have this settlement scale risk model in the works. In the works is the key phrase there. Hopefully we'll be reporting a bit more on that in the coming months. all the experimental data is eventually going to be made open source for other researchers to hopefully get their teeth into, whether that's just to use an educational tool or whether you want to go and, improve upon our analysis as they are at the moment. I'll be most welcome. I'd rather not do all that work again. So, if you are sitting here as a researcher and you have an idea of how you could improve like our TSE regression model, you're more than welcome to try that. And then hopefully we'll be publishing a paper still in the writing phase of the experiments, focusing on this sort of time to ignition mapping style of presenting the data. That's me. Thank you very much. There's another opportunity to thank everyone that was involved in these experiments, contributed, made them happen. Any questions? I know there's a lot popping off in the chat that I might need a second to just like read back the last few. And yeah, thanks very much. Please turn your cameras on and ask questions, or just put them in the chat, or wait and email me after. That would be most welcome. Dave, you've got your hand up.
Yeah, I just want to say thanks for that presentation, Sam, and thanks for kind of battling through the kind of coughing and the kind of sore throat that you're kind of getting through with all that
It's
talking.
just dry.
Just dry.
Talking for an hour.
I just wanted to come to Venki's couple of questions around the fuel load within the homes and try and kind of think about that a little more, and just kind of try and present some of the data that we have already around that, and kind of how that number of or the size of that crib came about. So I think in these experiments, the fuel load was around about 40 kilograms per meter squared of timber, which comes out to be about 700 megajoules per meter squared in terms of fuel load. So that's for your nerdy fire people. That is kind of based on a few different inputs. So the Eurocode value for the kind of energy per meter squared, the megajoules per meter squared, for dwelling is 780 megajoules per meter squared on average, with a kind of upper band of 948 megajoules per meter squared as the 80th percentile of that. So they do some statistical work to get these distributions, and the mean is 780, and then the 80th percentile is 948. So they, within the Eurocodes, if you're doing this for a high-rise building, you'd have this kind of variation of fuel load and heat load within the structure. Obviously, that context is not within informal settlements, but there are a couple of pieces of work that we do have from one from Stellenbosch University, where F. Marie, a master's thesis student, looked at some of the data and found that through their kind of analysis, a fuel load of 420 megajoules per meter squared with a 530 megajoules 80th percentile like 80th percent fractile value. So that's the upper band. Recently, we're just processing some data from the Iris Fire project, where we looked at 600 homes in the Western Cape, and we've got we're in the process of publishing this, but we had around about 850 megajoules per meter squared. So the fuel load that was used within these experiments was very much representative of what we see within informal settlements. Now, obviously, there's going to be a huge range in that, and we do need to understand that. When it comes to your second question about how the fuel might change the way things go, the initial stages of the fire in terms of the growth phase of the fire before we get to that steady state. So if you remember, Sam showed one of these curves where the mass loss rate was around about 0.5 kilograms per second. That is dependent on how much ventilation, how much doors and windows you have allowing air to come into the compartment. So when you get to that steady state burning, what the material is doesn't actually play too much difference. It's only in the early growth phase where we have that kind of concern. And so, yes, some of your points there about the real life shelters and things inside there in terms of vulnerability and the initial growth phase will be very important. But the overall hazard work, the types of material that you have in there, are slightly less important. Obviously, I'm excluding in that things that could explode, like gas canisters and things that can suddenly release a high volume of energy in a very short space of time. They can dramatically change how fires spread, but that's a whole different question. Yeah, Sam, I'll let you get back there. I hope hopefully that's kind of answered a bit of your question there. Thank you.
Yep, thanks, Dave. Yeah, any more? I've got a hand up from Raphael. Do you want to say hello, Raphael, and ask a question?
Hello, Sam. Good morning.
Hello.
I'm trying to put on my camera. I don't know if you can see. Not yet. I'm sure. Okay, good. Yeah. So thank you very much for the great presentation. Quite exciting. I just want to point out something. I mean, just a comment. You mentioned about firebrands quantification earlier, that you couldn't do that, and of course, it's I mean, quantifying firebrands in large scale experiment and all of that, it's actually challenging and all of that. But there's a work that was done at WPI, Fire Protection Engineering, by Fernando, a PhD student. I think it developed, not developed, it used a UNet algorithm for the quantification of firebrands. You know, we used an intermediate scale wind tunnel where a kind of, you know, measured measured firebrands that have been produced. Maybe whoever is interested on this call may take a look at the paper that was published in Elsevier. I think it's detection, quantification of firebrands using UNet detection algorithm. So I just thought of dropping that. So my question is about gas emissions. You know, of course, we know how when it comes to sustainability, this is very important. So I don't know if by any chance I know you didn't do because you didn't talk about it, but maybe you intend to look at that in the future, you know, just to quantify gases. I don't know if you can comment on that. Yeah, thank you.
Are you referring to kind of like gas toxicity or temperatures? Yeah, that would be helpful.
Yeah,
clarification.
yeah. I mean, gas toxicity, because of course, even if I'm talking about sustainability, if it doesn't affect people, of course, the smoke will play a lot of role, like talking about the CO2 or even the PM 2.5, you know. So yeah.
Yeah, nothing in these experiments. Dave, I know, didn't you have gas analysis potentially in some of the iris experiments that might have been just, maybe I'm misspeaking, but yeah, I mean, it's an interesting question because really with tenability, when we're talking shelters that are generally quite small scale, you know, there's tenability from the fact that if there's someone inside, and this is, you know, not a nice conversation to be having, but if there's someone inside there at very close range of the heat source, so radiant heat, direct flame contact, the hot gases anyway. I mean, we could look back at our data and see what gas temperatures are we picking up at different heights, and therefore how quick would we expect a smoke layer to be descending inside the shelter. But in terms of like the particular chemistry of what the gases are, nothing in these experiments, and I'm not sure they'd be particularly helpful anyway because it's just wood chip burning. It'd be far more interesting if we have like real fuels. By interesting, I mean nasty when you start introducing synthetic materials, and you know, might have a lot of horrible byproducts. But I mean, toxicity stuff is not really my area. But it's certainly an interesting question in terms of, okay, if a fire starts in one of these houses, how long do people have? I think the easy answer is not very long. Yeah, I noted a comment. I noticed there's been some back and forth about the 30 meters on the chat at the side. Yeah, I'm looking at, I think it's Scott Danish. I hope I got your name right there. But so in camps, you're finding growth dynamics are akin to wildfire dynamics. Yep, I agree with that's the sort of direction they head, but it depends what we mean by wildfire dynamics, because that is a huge range of scales and different behaviors that are going on there. Again, this 30 meter fire break to me seems like, is it a question of trying to stop firebrands? If it is, it's probably not enough. Is it trying to stop radiation and flame contact? If it is, it's probably far too much, because there's a researcher called Michael Gollner who's done a review of hazard conditions a few years ago now, like hazard conditions in wildfires, and if it's looking at ignition by radiation, they're talking about even if you have a fully involved crown fire, which is huge scale, probably bigger than we're going to get from any settlement. We're still talking about fire struggling to spread over. I think anecdotally, it's like it can spread across 10 meters, maybe 50% of the time. At 20 meters, it doesn't really spread anymore. So this 30 meters number is conservative even for wildfire management in terms of radiative spread. Again, if it's all about firebrands, then that's maybe a different conversation. But I see you've got your hand up. Sorry, Scott. Do you want to chip in?
Sure. Good day, and thank you, Sam, for a wonderful presentation. I should allude, now I'm in a different position, but previously I was the USAID International Wildfire Coordinator for 20 years. And so all of our work mostly was, of course, all was international, but a lot of it is less to do with wildfires, but more to do with wildfire's effects on settlements, in developing countries, much like, unfortunately, what LA, our own city, has seen last year, which we've had for years on the international side. But one of the, I guess, key points I wanted to ask on, a lot of this, I guess all the studies you did showed flame growth inside of a structure where you have, of course, you're surrounded, you have what's a containment of the radiative heat, versus if you looking at flame impingement from a structure, does material ignite the same way? You have, looking at some of those models you showed, that radiative heat was, especially with the bamboo mat, was pretty strong, 2 and 3 meters out. But would that material actually combust if, it was 2 minutes at a certain degree, external versus, where you have heat built up inside of a contained, dwelling? I was just curious if you did any modeling on that, just again, from our standpoint, where this is the cross we're finding here in the U.S. now, even in my current role back in fire management domestically, is the idea of, somewhat, I think my colleagues from the National Fire Protection Association are on, but the ideas of fires starting internally in a house versus going from house to house or settlement or structure to structure, how that works with, again, the structure at that point becomes no different than, in our view, like a tree. And so it's just what is the radiative firepower and what is the flammability externally of that other structure?
Right. I love this question. So I want to just clarify. So I'm kind of hearing that as like, okay, we're measuring heat flux, but we're not necessarily measuring direct flame contact, and we might be measuring a remote heat flux that's actually distant from the fire. Is that correct?
Yes, I mean both. I mean, just because we find, for firebrands, we don't have any flame impingement. Most homes in the United States aren't burnt because of flame impingement. It's firebrands or radiative heat. But that said, we in shelter, in settlements, we have both.
Yeah, right. So, I mean, I guess with our analysis, we're erring conservatively because we're saying a heat flux profile is the same regardless of whether that is like, so for the sake of argument, I have 2 heat flux profiles. One of them is generated, they're exactly the same in terms of values, but one of them is generated by purely radiative heat transfer, and one of them is generated by flame impingement, where we have direct flame contact. Again, they're the same, like quantitatively, they're the same amount of energy being transferred, but the difference is that radiative heating might not have a pilot source. Now, we're conservative because our ignition data uses piloted flame, right? So I think, like, optimistically speaking, I'm making these analyses and I'm saying at X distance, we're expecting fire spread at this amount of time. The reality is hopefully that it's actually a bit less. But the impact of sorry, to be clear for other people on the call, that's because when we're trying to ignite a solid material, it's releasing fuels to the surface. We need those fuels to have enough energy at the surface to ignite, and if we have direct flame contact, we have that pilot source immediately at the material. Anyway, if we're just experiencing radiation, there might not be a pilot source in the fuel gases to cause the ignition of the material. So because our ignition data assumes piloted, and we are conservative, but the kind of catch is that the higher and higher you go up in heat flux, the less a pilot source matters, to the point where you essentially get convergence where piloted or unpiloted, a material is going to ignite in 20 seconds or something. So I think I'm maybe sort of straying off where the core of your question. Anyway,
I think you nailed it, and I'm sorry to
okay.
to throw out a long-winded question at you at the last minute.
And I guess I would love to. We tried doing some sort of visual flame analysis, actually with Wojciech at ITB, and getting them to do some image processing to say, well, actually, where in space is the flame at any given moment? So can we combine the heat flux profile with an indication of, yes, there is flame present or not? Unbelievably hard to do in large outdoor experiments. Like if you're in nice controlled lab settings where you can control the lighting and between experiments it's all consistent, sure, easy, you can track your flame. If you try doing that outside when you've got people wandering around, and we had little things like there was orange cones on site, and when we tried analyzing the imagery for flame presence, then we're picking up like a cone or someone's car or all these kind of ridiculous things. So yeah, I mean, it's a kind of a hole at the center of the data at the moment. Is it piloted? Is it not piloted? How much does that matter? But certainly in the short range, I think some of the heat fluxes we were seeing off these are like, it doesn't matter if it's piloted or not. It's like 50 kilowatts per meter squared plus. And at that point, that's maybe a 5-second difference in your ignition time. But yeah, who knows? Thanks for the question, Scott. It's really, really good. Are we finishing up, Jenny? Is this
No, we are able to go on. We've had this in past COPs where I've just put a note there that if anyone does need to jump off, we understand we're at the time. But for anyone whose question has not been answered yet, we can stay on for a few more minutes. Scott asked one of the first questions. Scott, was your other question answered? Right up.
It was looking. This was based on some previous work at USAID. I'll leave the country out of it, but we were monitoring some intentionally lit fires in IDP camps by the government, and so doing this remotely. And so we're using fire radiative power to determine doing our best to determine like the size of structure, the number of structures burning, using satellite imagery too. But we were trying to demonstrate that, these people were being burned out of, intentionally being burned out of their camps. And so anyway, not related to this, but just the idea of using fire radiative power, using VIIRS and Sentinel, just to determine the heat sources when you have a large camp burning. And you can get in, if you know the size of it, theoretically you could get mass, et cetera. So not to belabor it.
Dave, you've got your hand up again.
Yeah, I mean, it's just to kind of come in on that conversation about VIIRS and things. I think it works when you get to a certain scale, obviously because of the spatial fidelity of the satellite imagery and the data it's using. And there's a question of like, if it's got to that scale, is it already too late? I think that there's the mapping and understanding what's going on versus the kind of, can we understand the science? So I think we need to come together on both those aspects. How can we use the satellite imagery in near real time as much as possible with some of that fire science stuff that's the fundamentals to come up with these risk mapping exercises and methods so that we can come into camps and help manage and plan so we can reduce the fire risk. So yeah, it's I like VIIRS, but it's always one of these data sets where I'm like, well, you know, do we get enough fidelity on the actual fire rather than there's a big fire happening? And maybe some of that kind of information that you were talking about there in terms of how you can export some of that information, or yeah.
It does sound like, for years, I believe it's 375 meters square, but I think it sounds like with some of these other startups that are sending up, low orbit satellites that we're looking at, at some point like 10 meters. So, theoretically, it will be able to pick up very minute, single or multiple dwelling fires.
Yeah, thank you both. Sam, I'm just going back just to make sure we haven't missed any of the other questions. I'm seeing a question. Yeah, and just correct me if you haven't already covered these, but there was a question from Paul reflecting on his time in Bangladesh. Humidity, he says, humidity played a key part in flame length, which was a key component in fire spread. Did you somehow allow for this? I mean, we had lots of humidity and lots of rain.
Indication of, oh yeah, okay, humidity. Did we allow for it? Well, generally, I think everything we were using, all the materials had been kiln dried to reduce moisture content, because we're always going to get worst case in really, really dry conditions. Oh, Paul, I see you've got your hand up. Do you want to maybe ask if that's to clarify the question?
Yeah, hi. Oh, sorry, you're on that screen, aren't you? I'm looking at different screens here. Sorry. Hi, Sam. Yeah, so one of the things that we found was relative air humidity. So we did a number of fires for training purposes throughout the year, and certainly, when the humidity was high, the flame length was much shorter, so therefore flame spread was much more complex, and much slower. And then when it was, when the humidity was low, we had much longer flames, so the spread was going to be much quicker. So I didn't know whether you'd conducted your experiments over a period of time where you had differing humidities, because that would obviously affect the heat flux that you're getting out from the flames. So that was essentially it.
Yeah, no, it's a great question. It's not, to be honest, it's not something we tracked. I think we, generally speaking, we're always testing in the gaps in the weather that were like nice and clear and dry. Having said that, we did have this big spell of rain that basically washed us out of sight for 2 weeks. I think we didn't do any tests at all. So it'd be interesting actually to look back and see if the experiments that came after that were maybe more affected by moisture. I'm not sure. But then again, it's like, because each experiment was different in the first place, we don't know if the impact is due to humidity or the materials. But certainly the impact of the materials is going to dominate. And as I said, all our materials were dried. So the only time that they would have had to sort of gain or lose moisture is in the time that we're actually built the shelter and burned it, which is not a long period. We generally turn it over in a couple of hours, maybe a bit longer. But I like the question. It's certainly an interesting point, and I think generally just to be wary that fires are always going to be worse in drier weather. Being analytical, like specific about that's quite difficult. But I know Imperial have done work recently looking at like vapor pressure deficit and how periods of elevated temperature and vapor pressure deficit are a very, very good indicator of periods in which fire spread is going to be exacerbated. So yes, there are sort of meteorological metrics that you can be tying fire risks to, that we can even think about, like maybe we can build that into models. It's hard to say exactly, okay, what the correlation between humidity and flame length is. That's a very, very difficult question to answer, right? But It's obviously there. We just haven't measured it. Yeah. Dave, you've popped another question, have you? Oh no,
And
I'm just at a different point in the chat.
yeah, there was also, just while we're on Paul's questions, there was one other question from Paul about the tarpaulins. How would the tarpaulin shelter behave if the contents ignited and developed quicker, as would be the case with finer fuels or more flammable materials such as plastics?
I think that's maybe Dave. Did you kind of answer that already?
Sorry.
Kind of. Well, I mean, there's two ways of. Well, I say it's two ways of answering that. No, I'll answer it in one way, and that's like if you have a faster going fire, with the specific experiment that we had, where as we're talking about fuels like not up against the tarpaulins, we've got fuels kind of like in the center of the floor space. The difference is if the fire grows quicker, we reach in the smoke layer above the fuel, we reach whatever temperature it is that causes the material to warp and fail quicker. So I don't know if it's a question of, okay, if the fire goes faster, that means the tarpaulin is more likely to ignite. I think it's if the fire goes faster, the tarpaulin is going to exhibit those same behaviors, but they're going to start earlier because it's going to reach those temperatures faster. I think that's how I would answer that question. Any more?
I think we've covered everything. I'm scanning back through. Some were answered in the chat. And if anyone feels that their question wasn't answered, this is a great moment to put up your hand, and we'd love to hear your voice so we don't miss anything. Oh, Danielle asked, what do we mean by fire-resistant materials in Sphere? Sam, can you just touch on that? I think that might be the last one.
That's a great question. I'd love to know. Like, what do we mean?
Yeah.
There's like Sphere doesn't put a bound on that. It just says prefer fire-resistant materials with no kind of guidance as to like what that constitutes, because fire resistance is in some industries measurable with very, very defined sort of testing methods, as we've looked with like things like the SPI test, but other standard test methods that say this material is fire resistant to exactly a certain classification. So just the statement preferring fire resistant materials, like, yes, I know if I build a house out of brick, that brick is not going to burn, it's non-combustible, therefore fire resistant. But that's where it gets difficult, is there's this spectrum of, just because a material can burn, it doesn't mean, like, not all combustible materials are equal. So there's fire resistance is a massive spectrum. It's not kind of a binary thing. Dave,
Yeah,
put your hand up again.
I also think in terms of fire-resistant materials, it's also about the system that you build it in. You can have non-fire-resistant materials built into a system which is inherently fire-resistant. So, for instance, the PCM cladding that we've had in all around the world, if you build that into the system properly, it can be determined as fire resistance for a certain period of time, and that's okay. Designed for that. So there does need to be some clarification about what we mean by fire-resistant materials, particularly in the context of systems of different materials together. One of the things that we're trying to look at is that bamboo and plastic sheeting combination to understand how they impact each other as a system. And that is the next kind of step when we start thinking through these problems.
Well, thank you, Dave. Oh, I see one more hand. Okay, great. I think we'll have to make this the last, most likely. Scott, over to you.
Just one last point on the flammability piece. One of the things we're finding, unfortunately, very late, is for flammability and fire resistance. A lot of that is determined by PFAS and different chemicals in the material, which frankly is almost just as detrimental, especially for young folks in these shelters, as much as a fire is. Obviously not immediately and acutely like a fire, but the challenge is fire resistance in material that is not cancer causing, and also thinking about how the material is used, because there's lots of times shelter material is used for a table, it's used for all sorts of stuff, much less than just covering a shelter. So anyway, just more questions to be looked at. Thanks.
Yeah, that's a really interesting point, Scott. And I do not want to be the person to do that kind of cost benefit analysis, if you can call it that. We're trading off between fire resistance and horrible diseases. Like, that's not a nice thing to be thinking about. I appreciate it's something that we should be thinking about. And just interesting on this note is the CPAI test that I was talking about. It's a textiles industry test, right? And the only people that really use it that I could find apart from the humanitarian industry are the recreational tent sector. And I have found articles about this, like the idea of fire retardant materials in recreational tents. And someone actually has done the trade-off, like, but people who go camping, they've got statistics on, well, for for all the people in the north of America, there's been like 8 recorded fires in a 20-year period where the tents burned out. And it's like, yeah, sure, okay, you don't really need fire retardants in your tent if, like, you're talking about people camping up a mountain, not in a settlement environment. And so, of course, those vested interest, a big recreational tent, of course, push for no fire retardants. Not no fire retardants. They were pushing for a while for the CPAI test to be made easier to pass, because they wanted to be able to pass it without having to put fire retardants in their product. Or I think it was the certain parts of the tent they didn't want to have to put it through that testing method, because then other people have gone and researched, well, what were you putting in the tents, and are those hazardous materials, and can we connect them to diseases? So just a word of caution is that the other industry that is using the same testing method as the humanitarian industry is trying to make it easier and easier to get around that testing method, and to not have to use fire retardants. So very interesting question, really interesting question. Again, I don't want to have to be the one to answer it, unfortunately. Anyway.
Well, thank you so much for all the engagement, all the questions, all the comments, both in the chat and in real time here live. Sam, do you have any closing word or any last thought that you'd like to offer? Otherwise, I'll wrap up for us.
Not really. Thanks for coming. Appreciate you all taking the interest, and it's been a pleasure to present this stuff. It's been a long, many months of work through this data. And if you have any other questions, fire me an email or message on LinkedIn or something. I realize I should have put my contact details on the slide, but I'm sure you can find me other ways if you need to.
Yeah, thank you so much, Sam. From our side, as your Kindling colleagues, we are very grateful to you and the team for the incredibly hard work to get these experiments to happen and to analyze all the data. Yeah, thanks. Sam's email is in the chat. Thanks, Danielle. And we also will be sending out an email to everyone who registered for this webinar, so that you can contact us in that way as well. So from our side, as I posted in the chat, Kindling is incredibly grateful for the support from the Fire Safety Research Institute that made these experiments happen. We're grateful to our other collaborators. And yeah, we look forward to all those next steps that you mentioned, all the future work, all the work that's underway. And we do invite you to continue engaging with us and in upcoming COPs or in other ways. So thanks, everyone. Thanks for staying on. And we look forward to engaging with you further. Take care, everyone.